Okay, hello everybody. Today we're going to start with section 20, kinetics, and this is our first lecture on that. So this would be our introduction to kinetics. All right. All right. So kinetics. First of all, what we're talking about is looking at the rates of chemical reactions. Kinetics comes from the word meaning change, so we're talking about the rates at which the chemical composition of a mixture changes during a chemical reaction. Some of the places where this might be important in industry, if you are synthesizing sulfuric acid, for example, right, and you find that it takes you 3 hours in your plant to synthesize a ton of sulfuric acid. If there's a way you could speed that process up so that you could synthesize that same amount of acid in a shorter period of time, then you'll be able to increase the efficiency and you'll make more money, right? So rates of chemical reactions are important for industry. Pharmacy and medicine, of course, because we can talk about the rates of chemical reactions in a beaker, right? But we can also talk about chemical reaction in your body. And so understanding how drugs are metabolized. If you take a certain drug, can you take 100 milligrams every morning, or do you have to take 50 milligrams every 12 hours? Well, that depends on how that drug is processed by your body, right? And we can also think of the environment, environmental chemistry. You know, if you have a pollutant in a stream and that pollutant is gradually degraded over time, maybe when it gets hit by sunlight, those molecules break apart and eventually the pollutant is cleaned out of the system by decomposing. Knowing how quickly that decomposition happens is really important, right? This was one of the problems with DDT back in the 1940s. DDT was a really useful compound for combating mosquitoes and other insects and things like that. But the problem was it decayed very, very, very slowly. So once you got some DDT in the environment, it stayed there for a very, very long time. And that allowed it to pollute streams and eventually pollute wildlife and things like that. So kinetics is important for understanding how things behave in the environment. Okay. And we can come up with a bunch of other things as well, but those are just a few examples. All right, so if we want to talk about how we describe the rate of a reaction, we can compare this, I think it's useful to compare this to what we would do in physics. We talk about changes in position in physics. We call that velocity or speed. And so if we have a car that's driving from left to right across your screen, we want to say how far the car is going. We could measure its position here. We call that x1. Measure its position here. Call that x2. And then we could use a stopwatch or something to measure the time at which the car was right here, and look at the stopwatch again to measure the time at which it reaches the second mark. We can call that t2. So the speed then is the rate of change in that x coordinate. We use capital delta for change. So the change in the x-coordinate divided by the change in time. Right? And the change in the x-coordinate is just x2 minus x1, right? That's the change in the x value. Right? Divided by the change in time, which is t2 minus t1. Right? So that's how we would define speed. I think that's pretty intuitive, right? So we can do the same thing for a chemical reaction, except for the reaction, of course, is not moving. Okay. So for chemical reactions, we define the change as the rate or the rate of reaction. And for so the rate is the change in the chemical amount divided by the change in time. So you measure the amount of stuff you've got at one point, you check the time, you wait a few seconds later, check the time again, and check the chemical amount, right? And the difference of the two values of the amount of stuff divided by the difference in time is the rate. Okay. Now the chemical amount could be in moles, right? In which case you take the moles at time 2 minus the number of moles of stuff at time 1. Right. And divide by the time at the end of the experiment minus time at the beginning of the experiment. Right. So this would be your change in time, and that would be your change in the number of moles. Right. But since we do things in solution a lot, you can also do this in terms of concentrations, right? So instead of just directly measuring the number of moles, we can just measure the concentration. So this would be the molarity at time 2 minus the molarity at time 1 divided by the difference in time, right? All right. Terrific. And you could, I think there's some examples like this in the textbook. If you're doing a reaction in the gas phase, you could also do this by measuring the pressure change over the course of the reaction. So you'd have pressure at time 2 divided by the pressure, or minus pressure at time 1 divided by the difference in time between those two measurements. All right. All right, let's take a look at an example. All right, so this is NH3 ammonia reacting with aqueous acetic acid to give ammonium ions, NH4, plus acetate ions, C2H3O2 minus. This 2 doesn't look like a 2. Let me fix that. There we go. All right, so let's look at how various species change over time. if we plot the concentration of ammonia over time, we'll start out with some amount of ammonia, and as the reaction proceeds, because the ammonia is a reactant, its concentration is going to decrease. Okay? And a typical curve for the decrease in concentration of reactant looks something like that. Okay, so on this graph, that'll be our line. Okay, use a dotted line to plot the concentration of ammonium ions as a function of time on the same graph. Okay, think about that for a minute and then sketch it in. Okay, since ammonium is a product, when the reaction begins, there isn't any ammonium ions, so it'll start at 0. Okay? And as the reaction progresses, it will be producing more ammonium ions, and so that concentration will gradually increase. And as this goes down and then gradually kind of tails off and asymptotically approaches 0, ammonium is going to look like that, gradually increasing and then asymptotically approaching this value here, right? Because the number of moles of ammonium at the end has got to be the same as the number of moles of ammonia that you started with. Okay. All right. And we could define the rate for ammonia at some point on this graph by just taking 2 points and looking at the change in concentration over that range and the change in time. So here's T2 and here's T1. Here's molarity 2 and molarity 1. Right? So the change over that period is the rate of change for ammonia. Notice over the same period, the change for ammonium is going to look very similar, right? Except that ammonia is decreasing and ammonium is increasing, right? Now that's important because it's always going to be true for reactants that their concentration decreases over time. So if we look at changing concentration over time, we're always going to get a negative value for reactants because they're decreasing. For products, their concentration is always increasing, and so the slope of this line is always going to be a positive number. Okay? Because we want to, let me back up a little bit. So we can define the rate of this reaction as the change in the concentration of ammonia as a function of time, right? Or we can define this as the change in the concentration of ammonium, this product, divided by the change in time. Okay. But this is where I was going with the comment I was about to make a minute ago. We want to define the rate as a positive number. Whenever we give the rate of a reaction, we want that to be a positive number. But this slope is negative, right? So for reactants, we're going to put a negative there. Okay. So when you calculate this number, you get a negative value for the slope, but just change the sign for the rate so that the rate is positive. For a product, if you calculate the change in concentration divided by the change in time, you'll get a positive number. Okay. All right. Let me show you another similar problem. So we're looking at molecular chlorine, Cl2, breaking into 2 chlorine atoms. And if we plot the concentration of molecular chlorine over time, that concentration will decrease like that, just as it did for ammonia in the last problem, because this is a reactant, so its concentration is decreasing. Take a minute to plot the concentration of atomic chlorine, Cl. Take a minute to plot that concentration as a function of time on this graph. All right, so the atomic chlorine is a product, which means initially its concentration is 0 and it's going to increase over time. Okay? But unlike last time, it's not going to increase like this and even out at the same concentration that we started with, because every 1 mole of molecular chlorine that decomposes gives us 2 moles of atomic chlorine. Right? So the amount of atomic chlorine that we end up with is twice as much as the amount of molecular chlorine that we started with. So it's going to look like that instead. And you can see again, if you measure the rate here at some point and measure the rate here at some point, this rate, or this change here, the slope is negative, this change here is positive. But what's different is now, you see this slope is fairly small, this slope is very steep. Okay? Because if you look at this reaction, you can see this has to change twice as fast as this does. Okay? So if we do the same thing we did before and define the rate as the change in concentrations over time, because molecular chlorine here is a reactant, we have to put a negative sign here. Okay? And then, because this one is changing twice as fast as this one, we have to put a stoichiometric coefficient here, and we're going to put this way with a 1/2. Okay. Which, what we were saying before is that this is changing twice as fast as this. Writing it this way says that this is changing 1/2 as fast as this, which is essentially saying the same thing. Okay. So, with that being the case, I'm going to show you how we can, in general, define the rate for any reaction. So if we have a reaction that looks like this, where we've got A plus B goes to C plus D, A and B are the reactants, C and D are the products, and these lowercase letters represent the stoichiometric coefficients, then we can define the rate this way, right? Where the rate is change in concentration of all of the species divided by the change in time except that because these two are reactants, their concentration is decreasing over time. We want the rate to be a positive number. So we'll put a negative sign in front of our reactants. And then to account for the fact that the rate of change for all of these is going to be impacted by these stoichiometric coefficients, we put a fraction in front of each one, 1 over the stoichiometric coefficient. Okay. All right. Now, I wanted to put this up here because it's in the textbook. It's in all of the textbooks. They all do it this way. And this is correct. You know, this is the way you ought to think about these things. But it's really kind of, it seems really kind of needlessly complicated that way. One of the things you can do with this equation is if you understand the rate of change, or if you know the rate of change for one species, you can use this to calculate the rate of change for another species. And you can do that using this equation, but it's a little bit tedious and cumbersome. Turns out you don't really need to do all of this to look at the rates of change for different species in a reaction. If you've got your balanced equation, then that will really be enough. And let me show you how that works. All right. So let's say we are reacting nitrogen with fluorine to make nitrogen trifluoride. And our stoichiometric coefficients are a 1 here, right? Remember, if you don't put anything there, that's understood as a 1, a 3 here, and a 2 here. So, in case you can't read this, I'll read this out to you. It says, if fluorine, F2, that's this, if fluorine is consumed, because it's a reactant, if it's consumed at a rate of 2.5 times 10 to the minus 3 moles per minute, what is the rate of production of NF3? That's our product here. Okay. So, we can start with what we know. We know that 2.5 times 10 to the minus 3 moles of F2 per minute are consumed, and we want to know the rate for NF3, right? Well, we've got these stoichiometric coefficients here, right? So we know that for every 3 moles of fluorine, we're going to produce 2 moles of NF3. So we can write this, I'll put this over here for a second. We haven't done stoichiometry like this for a couple weeks, but remember, we can write 3 moles of fluorine equals 2 moles of NF3. And so we write that as an equation. Okay, hold on just a second. Okay. So we've got this equation based on our stoichiometry. 2 moles of fluorine is equal, or 3 moles of fluorine is equal to 2 moles of NF3. So that means that we can write 3 moles of fluorine over 2 moles of NF3 is those things are equal. That's a fraction that's equal to 1, and therefore we can use that as a conversion factor. And we could also take the same thing, flip it upside down, and use it like that as a conversion factor. All right, so in this case here, if we want to convert this rate of fluorine, moles of fluorine per minute, to moles of NF3 per minute, we'll just use that conversion factor that we had. But we got to make sure we put fluorine, we got to put the F2 on the bottom. So 3 moles of F2 is equal to 2 moles of NF3. Okay. And those cancel out. We're going to end up with about 17, I think. So we end up with 1.7 times 10 to the minus 3 moles of NH3 per minute. Okay. All right, lovely. Let's keep this same reaction up here and do a second question. I'll put this up here and let you solve this on your own. All right, so we'll start with the same premise. If fluorine is consumed at a rate of 2.5 times 10 to the minus 3 moles per minute, so fluorine is consumed at a rate of 2.5 times 10 to the minus 3 moles per minute. What is the rate of consumption for ammonia? Okay, take a minute, hit pause if you'd like, take a minute, work on that problem, and then when you're done, unpause it, and you can check. I'll put my solution up here on the board. Okay, so I did this the same way last time. We're comparing the rate of fluorine and nitrogen. So I wrote down this little stoichiometric relationship. 3 moles of fluorine equals 1 mole of nitrogen. So I can use this as a conversion factor. I want to change moles of fluorine to moles of nitrogen. So I'll put 3 moles of fluorine down here, and 1 mole of nitrogen up there. Let's cancel out. And that gives me 8.3 8.3 times 10 to the minus 4 moles of nitrogen per minute. All right, lovely. Okay, that's good. Let me see if there's something else. Okay, that's good for introduction. We'll have some other videos on rate laws and things like that in a little bit, but this is a good introduction video. Take a look at this, work on this, and look at the study guide and work the study guide chapters and the end of chapter problems in the book. And I will see you again soon. All right, see you everyone.